This is Premjit from civilara.com. In this module, we will discuss when to do dynamic analysis. IS 1893-2016 clause 7.7 tells you when we have to do dynamic analysis. Dynamic analysis shall be performed for all buildings in seismic zones 3, 4 and 5. For all regular buildings more than 15 meter height in seismic zones 2. For all irregular buildings in seismic zones 2. So this means that only buildings which are less than 15 meter in height we can do static analysis. That too in zone 2 alone. In zone 3, 4 and 5 all buildings we have to do dynamic analysis. Now what do you mean by regular building? A regular building has simple geometry like a rectangle. There will be no offsets in plan or height. There will be no load variation in plan and height. There is no stiffness variation as well. So basically a regular building means it is very regular in nature in terms of its shape, geometry, height, the load variations and the stiffness. Less the complication, more the stability. And when the complication in the geometry and the stiffness variations and load variations are less, the damage during earthquake also will be lesser. So let us adopt this principle: less is more. Lesser the complication, more is the stability. Now let us define and understand irregularity a bit better. Now horizontal irregularity. This is mentioned in table 5 in IS 1893-2016. Now here you can see the horizontal irregularity of buildings. Here you have an L-shaped building. Here you have a Y-shaped building. These are all planned geometry. Here you have a kind of H shape. Here you have a lot of offsets and it's like a plus sign, and here you have a T-shaped building. Now the problem with these buildings are that the load path is not direct. Here if this column and if this column, if there are two columns or two structural members across this, and if this has to interact, and that will interact because the entire building is tied by beams and diaphragms, so these will be interacting definitely, but there is no direct path between this. So this will induce a kind of torsion in your building when there is ground movement. Ground movement is nothing but earthquake induced movement. When the ground moves, the inertia forces the building to stay in place, and this creates a kind of displacement in your building, and this displacement becomes a force in your building. This is how earthquake, or this is how a lateral force is induced in a building due to earthquake. So these irregular shapes aren't good. These are not going to help the building when there is a ground movement. So the best option to do is to separate these legs into different parts so that these are all independent buildings. When I say separate, by providing joints, you can structurally make these buildings two. Say for example, you provide a joint here so that this part is treated as one building and this part is treated as a second building, and they behave independently structurally when a lateral load occurs. So this will make two simple geometry, two regular buildings rather than a single irregular building. So this is what plan irregularity is in, and that is one of the better ways of dealing with plan irregularities. This building can be split into three different parts and this will behave better. Or you can even put it like two different buildings, one gap or one joint here, and this will become one building, and this entire thing will become second building. So that way also you can separate the building and achieve regularity. Now second case, vertical irregularity. Again table 6 of IS 1893-2016 talks about this. Here you have the same kind of irregularity in the height of the building. These are all heights. Now here again you can separate these buildings in some cases, because here you have a say you have a tower and then you have a parking, something like that, and here if you induce a joint and here if you induce a joint, this can be 3 different parts or 3 different buildings, and then it is regular. Now when you have a lot of offsets like this, it may be practically not possible to induce or introduce so many number of joints in your building. Here it's a cantilevering structure. At the lower level you have lesser dimension, and in the upper level you have larger dimension. So it may not be possible for separating these buildings into different. Let's discuss what is torsional irregularity. It's a kind of horizontal irregularity. When you say a building is torsionally regular, that means that the building does not twist when stiffness distribution of vertical elements is balanced in plan according to mass distribution in plan. The floor slabs are stiff in their own plane. Generally this occurs when length by width of the building is less than 3. So when the length by width of the building is less than 3, generally the building is torsionally regular. Now when a building is torsionally irregular, the deflection at one end of a floor is 1.5 times that of the other end of the floor. Time period of fundamental torsion mode of vibration is more than first 2 translational mode of vibration. This means that the first or the fundamental torsional mode vibration, the time period of that mode is more than the first 2 translational mode of vibration. Now, what is the solution? Now, this is the first case wherein you have deflection at one end of a floor is 1.5 times to 2 that of the other end. So here, if you see here, if the deflection at this end of the building is delta, and if this end is 1.5 or 2 delta, that is if you have 20 deflection here and 40 deflection here, what do we do is the question, or that is what we call as one of the torsional irregularity. So if the deflection ratio is 1.5 to 2, the configuration to be changed to ensure time period of torsional mode is less than first 2 translational. And if the deflection ratio is more than 2, the building configuration should be completely changed. Now here we are going to talk about re-entrant corner and how is it going to create horizontal irregularity. When the plan has a projection of size more than 15% of its overall plan dimension. So here these are all offsets. So here also this is a L-shaped building. Now L1 and A is an offset and L1 is the total length of the building. So if A by L1 is more than 0.15 or if A by L2 is more than 0.15, then we call it is re-entrant corner and it is a horizontal irregularity. So 15%, that's what it means. Here also these offsets, if it is more than 15% of its overall plan dimension, then we call it re-entrant corner, and this also can create a kind of torsion in your building, this L shape. One solution we already discussed, that is we can introduce joints in your building and make it 2 separate regular buildings. But many times and every time this may not be possible. So we may have to do 3-dimensional dynamic analysis in such cases. That's a solution suggested by the code. Reconfiguration by providing separation joints and structurally separating the building is one of the best solution, because then we get 2 or more regular buildings. Diaphragm discontinuity or excessive cutouts in your project or in your floor plan. When more than 50% of the slab area, that is if this is your slab area, if you have more than 50% which is a cutout, then we call it discontinuity in diaphragm. Opening results in flexible diaphragm behavior and lateral force is not shared by frames proportional to its stiffness. More significant when openings are near edges like this. So if your area is more than 50%, in this case where the opening is in the center, and if the opening is more than 0.1 times the total area, in this case when the cutout is in the edge, what happens is, due to the presence of cutout, proper interaction between the structural members on one side of the cutout and the other side of the cutout doesn't occur, and this is why we treat this as a irregularity. Proper load transfer, lateral load transfer doesn't occur. If less than 50%, consideration based on location and size of opening. That is the thing that we have to do. If more than 50%, then slab to be considered as flexible. Out of plane offsets. This occurs when vertical elements, columns or shear walls are moved out of plane in any floor. So this is a classic example here. See, you have a continuous column, but if it is not given like that, and if it is stopping, and if you have a transfer beam, and then if you have a floating column kind of structure where the continuity of the wall or a column is changed, this is called out of plane offsets. Now in zone 2, special literature to be referred. That's the Cordell provision for out of plane offsets. In zone 3, 4 and 5, drift, that is the story drift due to lateral forces, shall be less than 0.2% in floor having offset and in the floor below. Also special literature to be referred. So here the drift between this floor and the next floor should be less than 0.2%. That is one mandatory clause that code tells you. Now, non-parallel lateral system. When vertical elements, that is columns or walls, are not orthogonal in plan. So here you have a non-orthogonality. Here your shear walls aren't parallel to each other. They are inclined to each other. It's not orthogonal, means it is not perpendicular to each other. They are not like this. They are inclined in plan. So what do you do when your structural members are inclined in plan like this? The solution is that building shall be designed for simultaneous effects of full design load in one horizontal direction plus 30% in other direction as per clauses 6322 and 6341 in IS 1893-2016. Simply put, that means that if you have EQX to be defined, EQX will be EQX, the real EQX plus or minus 30% of EQY. You have to take the effect of Y also, 30% in the other direction. Same way, EQY becomes EQY plus 30% in the X direction. So we have to do that if you have non-parallel lateral system. Now, vertical irregularity. This we will discuss in the subsequent modules.